Greetings, AP Chem. I hope that you had a good time trying to figure out electron configuration and kind of refreshing your memory a little bit. Hopefully that information is coming back to you. There are two things that we need to talk about today. One of them is some kind of weird stuff that happens with electron configurations when you get into the D shell. So we're going to get into that first, and then we're going to talk about orbit diagrams and paramagnetism and diamagnetism today. So hopefully this just kind of builds on some previous knowledge and solidifies what you learned previously. So as you can kind of see, you have the slide presentation introduction. I talk about some funny business with electron configurations because, like, honestly, life is boring without exceptions, and chemistry is just full of them. So you will know, I've seen like memes where it's like, oh, chemistry with exceptions, and it's like this big, and then, or without exceptions, and then chemistry with exceptions, the book is like that big. And that's true. You'll find with chemistry pretty much all the time, there are rules, and then there are like a bunch of exceptions to the rule. And so this is kind of the very first hint of those exceptions to the rule. So the first thing I want you to do is grab a periodic table if you don't have one of those out already, because we're going to go over this. Grab your periodic table, and then I would like you to predict the electron configuration for copper. So pause the video, get your periodic table out, and then on a scratch sheet of paper or in your head or whatever, I would like you to predict what you think the electron configuration for copper is. Okay, so I'll give you a second. Pause the video if you need to. All right, so my guess is that you wrote down your expected electron configuration for copper to be argon in brackets, because we're going to do the shorthand, 4s2 3d9, because if you count the positions for copper on the D block, you count it and there are 9 boxes over, right? Makes sense to me. However, scientists actually find out that the electron configuration for copper is actually argon 4s1 3d10. And you say to yourself, super. Okay, here's another example. I would like you to predict what you think the electron configuration for titanium 2+ would be. Okay, so again, take your periodic table out, pause the video for a second, see what you think the electron configuration for titanium 2+ is going to be. Okay. Hopefully by now you figured out that there's probably something weird, but the expected, my guess is your expected electron configuration, because titanium loses 2 electrons, would be argon in brackets and then 4s2. However, the actual electron configuration for basically any of the ions in the 3D shell is that they lose their 4s electrons first before they start to lose their d electrons. So in the case of the titanium 2+ ion, its electron configuration is actually AR, and then 4s2 is gone, and then the 3d2 is all that's left. All of the transition metals in that row do that same thing. So the 4s2 electrons are the first ones to go. Whether it's copper 2+ or any of those kinds of things, the first 2 electrons to go are the 4s electrons, even though when we fill in our electron configuration, you say to yourself, hey, yeah, so when I fill them in, it goes 4s2 and then 3d10 or whatever, because that's what you told me. Well, so the problem comes in with our electron configuration, because if you think about this diagram here showing the orbitals and their distances from the nucleus of your particular atom that you're looking at, the 1s shell comes first, then the 2s shell, 2p shell, 3s shell, and then 3p. And all of those, like I've said before, are kind of stacked varying degrees of distance away from the nucleus. But things start to get kind of messy once you get into that 3d 4s shell. So what we've said in the past is that the 4s shell is actually physically more distant away. But what happens is, almost in reality, the 4s and the 3d shell are very incredibly close in their distance away from the nucleus of your particular atom. So they are very close. And the other thing that's tricky about electron shells is that they are not like fixed. They are not set in stone. So the shell distance away from the nucleus is actually very dynamic depending on how many electrons are in there. So you can have a shell expand or contract depending on how many different electrons are in there, and it creates problems for us. Now, the College Board is not going to make you need to remember the unique electron configurations like copper, but they are going to ask you to remember that the 4s electrons are lost before the rest of the electrons when you take stuff away from a transition metal. That's something that they have asked in the past. And the reason why this actually happens, like I said, is that the 3D and 4s are very close to each other. So what ends up happening is that the 3D orbitals are actually ever so slightly lower in energy than your 4s orbitals. Again, very, very close. But the 3D orbitals are actually very compact and much more compact in the 4s. We're going to get into orbital shapes in just a second, and hopefully that'll make more sense in just a little bit. So what ends up happening is because the orbitals for the 3D are kind of very compacted with each other, what can happen is when we put electrons into the 3D shell, it actually makes an atom less stable than if we would pop them up just a little bit into the 4s shell. So the 4s shell is a little bit roomier. We have a little bit less stuff jammed in there. And so the 4s shell is the place that actually makes the element more stable. And we've talked about this in regular chemistry, that stability is the key. Your elements are going to do whatever they can to stabilize so they can maintain the state that they're in. And so what ends up happening is that in this case, the 4s electrons go the electrons go into the 4s instead of that very scrunched 3D shell where there's a little bit more room. And then in the case of the transition metal ions, because they're actually a little bit higher, what ends up happening is that if you take electrons off, those are the first two that come off of there. So for all of your ions that are in, let's say, the 3D shell, so like copper, and things like that, when they take their first electrons off when they're making ions, like in copper 2+, you lose the first two electrons. If we go back, if I would take this copper and turn it into copper 2+, its electron configuration would actually be 4s2, those little electrons gone, and then it would be 3d9 again. And again, crazy like transitions are happening in this situation. So there is electron fluidity between layers depending on what happens and what's beneficial for its energy stability. So just kind of something to keep in mind a little bit there. The other thing we need to talk about are orbital diagrams, and I actually think that this kind of helps clear up some of the weirdness a little bit. So when we're talking about an electron configuration, one of the ways that we actually show how electrons sit in an atom is by drawing an orbital diagram. Now, each of the orbitals that we're talking about are actually a mathematical equation or a mathematical equation brought to life that represents how electrons move around the center of your atom. So the pictures that I have here represent the different kind of orbitals that you see. The one underneath this S shell here looks like a sphere, and scientists theorize that electrons that are sitting in an S shell travel in a roughly spherical shape. And so what that means is that 90 to 95% of the time, you can find an electron that's assigned an S location, whether it's a 1s, a 2s, or a 3s, or beyond. They are going to be found in a spherical area roughly 90 to 95% of the time. Again, the nucleus is at the intersection here of the X, Y, and Z axes that you see on your screen. So all S's look like this. Each orbital can hold 2 electrons. So the S shell can hold 2 electrons because there is only one type of orbital that makes it up, and it's the spherically shaped orbital. Now, the P shell is a little bit more complicated. There are actually 3 different types of P orbitals. There's a PX orbital, which sits on your x-axis. There's a PY orbital and a PZ orbital, which kind of comes towards you in the screen. And what happens is if you think about each of these orbitals here as one of those things that makes up the whole P shell, these are all merged together. So if you can imagine, we've got one orbital going up and down, one going side to side, and one going front to back. They are all smooshed together. And then the S shell, that's the sphere, actually sits inside of the P shell. So it's almost like an onion. Your S shell, then another S shell, then those 3 weird P shells, then another S shell, and it just gets bigger and bigger and bigger. And so each of these purple p orbitals that you see here can also hold 2 electrons. And when we want to write an orbital diagram, we would represent them by drawing 3 boxes to represent these 3 orbitals. Now, the College Board is never going to ask you to draw these shapes at all. All you guys are responsible for are the boxes, which is a good thing. Okay? D orbitals. You would have 5 different shapes here potentially. They get a little bit more crazy and a little bit more complicated. But what you have to remember is that, again, these each can hold 2 electrons. So this weird kind of dumbbell shape with a donut around it, that can hold 2 electrons. This can hold 2, this guy can hold 2, this one can hold 2, and this last one can hold 2. And that's why the D shell can hold a total of 10 electrons. So when we do an electron configuration and then an orbital diagram drawing for it, what we do is we, if we want to draw a D shell, put 5 boxes down and represented for it. So when we're asked to look at an orbital diagram, what we do is we write the electron configuration first. So that's the first thing you need to do, is write your electron configuration. Then to draw the orbit diagram, what you do is you draw these boxes for each type of shell that's in your electron configuration. So if I am talking about hydrogen, hydrogen's electron configuration is 1s1. So all I'm going to do is I'm going to draw 1 box here, and then I'm going to label this 1S. So I'm not going to just call it the S block. I'm going to put 1S for this little box here. If you're feeling lazy and you don't want to draw a block, you could also draw a line, and that's okay. What you do then is to represent how many electrons are in that particular orbital. What you do is you draw 1 arrow up and 1 arrow down to represent 2 electrons. So if I just want to draw 1 electron in here, I'm going to draw 1 arrow pointing up. If I want to have 2 electrons in here, I'm going to have 1 arrow pointing up and 1 arrow pointing down. Okay? So if I'm doing an electron configuration, I get that figured out, and then I start to draw. So let's go through an example for, let's say, carbon. Carbon has 6 electrons in a total and has an electron configuration of 1s2, 2s2, 2p2. So if I want to draw an orbit diagram for it, I'm going to draw 1 box that represents the 1s shell. I'm going to draw another single box that represents the 2s shell, and I'll label it as 2s underneath. And then I'll draw 3 boxes that represent the 2p shell, and I'll write 2p underneath it. Then what I will do, since it's 1s2, I will put 1 arrow up and 1 arrow down in that particular 1s box. And the reason I do 1 arrow up and 1 arrow down is because when electrons fit into an orbital, they have a spin. They call it spin up and spin down. Now, are they really moving up and down? Not necessarily. But what happens is one electron moves in one direction, and when that happens, it develops a charge if it's moving in whatever direction it's moving. When another electron comes into that orbital, it moves in the opposite direction to counterbalance that other electron. So what they say is they call it spin up and spin down. So one electron is going one way and the other electron is going the other way. And it's always really hard for me to do this, but you have kind of an opposite spin going on. So they call that spin up and spin down. And that's why you have 2 electrons in there. Okay, so for carbon, the first shell, 1s, is going to have 1 arrow up and 1 arrow down. The next box that you drew is the 2s box. That's going to have 1 arrow up and 1 arrow down. The 2p shell should have 3 boxes, and it's actually kind of a unique situation. So when you fill your arrows for the p shell, they actually fill in 1 per box first before you start doubling up. And the idea is that each of these orbitals here has space for electrons to move around in it. But in an ideal situation, we put 1 electron in each orbit first to give the electrons their maximum amount of space. When you put two electrons together, they are both negatively charged and they want to push away. And when they want to push away from each other, it adds a little bit of instability. So if I can shove electrons into each of their own individual orbits first, that is better. I always use the example of, let's say you go on vacation with a sibling, and let's say you get to a hotel and you have a hotel with 2 beds and it's just you and your sibling on a road trip, because why not? So let's say you're on a road trip with your sibling and you get into a hotel room and it's got 2 beds. You are probably going to sleep one sibling per bed instead of having 2 together and then one empty bed, just because it's probably a little bit more comfortable for you. So you end up having 1 electron per box first. So in the case of carbon, I'm going to put 1 electron probably up pointing in the first box and another electron pointing up in the second box. When we draw our electrons spaced out in their own individual boxes, we call this the ground states for an electron. The ground state means it's the lowest possible energy combination that you could have. So if you have electrons that are in their own boxes and they're spinning in the same direction, and what I mean by that is arrow up and arrow up, that's the ground state. If I have arrow up and arrow down, that is a higher energy situation. If I have 2 electrons in one of the P boxes together and then nothing in the other 2, that's a higher energy situation because of the way that the charges repel each other. So the goal with these is to minimize that repulsion, okay? So here's what I want you to do. I would like you to draw the correct orbital diagram for sulfur. First thing you need to do is find your electron configuration. Then try to draw the orbit diagram. So what I want you to do is pause your video, do that, and then come back when you're ready to go. All right. Hopefully you figured out, or at least attempted this, and we will see how it went for you. So your electron configuration for sulfur is 1s2, 2s2, 2p6, 3s2, and then 3p4. So if I want to draw the full orbital diagram for sulfur, I'm going to draw 1 box representing the 1s, 1 box representing 2s, 3 boxes representing the 2p, another box representing the 3s, and 3 boxes representing the 3p. Now, if you wanted to do the shorthand where you have the noble gas, what you could do is you could leave off all of this 1s2, 2s2, 2p, and just put the noble gas neon in brackets and then start at 3s. So either way is fine. In this picture, they use half arrows, and honestly, it's just because it's a little bit faster. If you draw arrows up and down with both parts of the arrow, that's totally fine too. So what we do with the orbit diagrams is we fill in the 1s, because it's got 2 electrons, 1 pointing up, 1 pointing down. 2s is filled, 2p is filled all the way, but when I draw these in, I draw arrow up, arrow up, arrow up, arrow down, arrow down, arrow down. 3s is the same way, arrow up, arrow down. And then with the 3p shell, it's got 4 electrons in the 3p. So I'm going to put arrow up in the next box, arrow up. So you fill each of the p orbitals first, and then you start putting in the arrow down. Okay, so that's really the trick with that, is that you put the arrows down afterwards. So this would be the ground state orbital diagram for sulfur. If I had these 2 electrons here paired up together in 1 empty box, that would be, we call it an excited state for our electrons. Okay. Now, there is a property that is exhibited when we talk about, or that we can figure out when we look at our orbital diagrams, and it is called paramagnetism. So what paramagnetism is it's a kind of magnetic character that happens with elements that can be weakly attracted by a strong magnet. So if you take a strong magnet by a sample, if the substance is paramagnetic, you can actually take that substance and it's attracted to that magnet a little bit. Now, That comes from having unpaired electrons when we are talking about the orbital diagrams. So if I go back here, these two electrons at the tail end of this electron configuration here make sulfur paramagnetic. If I have any unpaired electrons, period, my substance is paramagnetic. And the more electrons I have that are unpaired, the stronger that magnetic character is. So that means that substance is more strongly attracted to that magnet when you bring it next to your sample. So if I had a sample of sulfur, that sulfur would be weakly attracted to that magnet. What happens though is, unlike something that's what they call ferromagnetic, like your traditional magnets that are always attracted to the magnetic things, when you take the strong magnet away from something that's paramagnetic, it is not going to be attracted to anything else again. So it's only attracted to strong magnets, but it's something that's kind of an interesting property to see. Sorry, you're hearing my dog bark back there. All right. The opposite of paramagnetism is something called diamagnetism, or being diamagnetic. So when something is diamagnetic, what it means is that all of the electrons have a spin up and a spin down in every single box, and there is no magnetic moment. You don't see it very often, but it's in things that have full shells and half shells. Okay. One thing that I wanted to kind of go back and just hit for just 1 second is our good old friend copper that we talked about. So copper, when you take a look at its electron configuration, we said that it is preferable for copper to have 4s1 and then 3d10 instead of 4s2 and then 3d9. So what you will find when we get into talking about things is that elements that have electron orbital diagrams where all of the shells are either full or they have half-filled shells, those provide kind of a easy set point for the energy in your particular element. So what I mean by that is copper having an electron configuration of 3d10 with all of these boxes having paired up electrons, and then a half-filled shell is more energetically favorable than if I had 2 in the S and then the D having 9 in them. So I'd have 1 unpaired electron here. That is better for copper. However, when I start to take off electrons for copper, then we start to take off the 4s electrons. So there's kind of this weird stuff that happens when you get into shells that are half-filled or completely full. They provide a little bit of extra stability that you don't normally see in something that's not half-filled or completely filled. We'll see that again very soon. All right, so here is your practice example before you go do your homework. What I'd like you to do is choose the orbital diagram that best represents the ground state of nitrogen. So get your periodic table out again one more time, pause it, and then see if you can figure out which one makes the most sense. Okay. If you figured out your electron configuration for nitrogen, it is 1s2, 2s2, 2p3. So first thing you can do to eliminate some of these is find the electron configuration orbital diagrams that do not have 7 electrons and knock them out. So if you look here, D only has 4, and then E has, 10? So those two, E and D, we can automatically drop out. The next ones, though, I believe have 7, so that makes it a little bit more complicated. Now, we know that our electron configuration is 1s2, 2s2, and those are going to be full up and down. So A and B have them full up and down. C has them half full. Now, if you look here, C has them 7 total electrons, but they are half filled. So what this is actually for C is considered an excited state for nitrogen. So now we just have to pick A or B and which one makes sense. And this is where the half filling rule is in play. So if you think about it, the 2p shell has 3 electrons. So I'm going to fill it arrow up, arrow up, arrow up first instead of doubling up. So A is the correct ground state. B is an excited state. C is an excited state. D and E are nothing. Okay? So go take a crack at your homework, see if you have any questions, and if you do, we will check them over in a Google Meet. Good luck.